Okay, so using this Newton-Raphson method then to solve this, the first thing we have to do is differentiate it, which is done here. Bring the power down, times it by the number in front, and take one off the power. If you remember, gives us this. In this case, x to the power 1, so bring the power down. 3 times 1 is 3. X to the 0, anything to the 0 is just 1, so 3. And constants disappear. So that gives us our differential. So now we apply Newton-Raphson. X0. Well, from our first guess, what we said last time is the first positive result was 4, wasn't it? And so, for our bisection method, our first one that we used was halfway between 4, which was 3. So let's start at that point and see how quickly we can arrive at the root compared to the previous method. So, start with, let x0 equal 3. So therefore x1 is going to equal x0 minus the value of the function at 0 over the value of the differential at 0. So for this case, equals x0, which is 3, minus, and so on. So as a little aside, I have to work out now what the value of the function is at 3 and the value of the differential is at 3. Plug them in. Yeah. Yeah. So on the calculator, x1 equals 3 minus, well, we know the function, so that's x cubed. So that's 3 cubed minus 3 times 3 minus 4 over the value of the differential, which we worked out to be 3 times 3 squared minus 3, wasn't it? Yeah. Lots of 3's. And I get an answer. So x1 equals just tell me when you've got it. Agreement? 2.416, presumably rounded to 4 significant figures. Okay, 2.417 to 4 significant figures. So let's go for 4 significant figures. Is that what we had last time? Was it 3 or 4 last time? 3, wasn't it? What do we do now? Put that value in. x2, our next guess, equals 2.417. Let me just, minus 2.417 cubed minus 3 times 2.417, I'm going to run out of room, minus 4 over 3 times 2.417 squared minus 3. Now, then you get x3. Record. Notice now, of course, we're actually homing on the value of x rather than getting 0, aren't we? Because we're not calculating the value of the function now, we're getting our next value for x. So what we're looking for now is when the value of x is not changing by more than a certain number of significant figures. So it gives us our x directly. Okay, so I'll just pause this and allow you to carry on. However, let me point one thing out to you before you do. So, looking up, did you get a different result, Carla? look at this on your calculator. Let's focus on this for a second. Here. If we use the brackets on the calculator, then we can actually, and if I put a bracket round here too, that number, that number, that number, and that number are actually the only ones I want to change in the calculation on the calculator. So if you put it into the calculator exactly like it is here, then you can go back and just change these numbers, not forgetting that one, and then hit equals, and it will give you the next root. So it just saves a little bit of calculator time to try that. So if I just pause for a few minutes, you can have a go and see if you can come up with the root and how many steps it takes to do it. So it looks like using that method, we end up with a root of 2.196, 2.195 to 4 significant figures after about 4 iterations. Was that quicker than the bisecting method? Right, so a bit quicker. Yeah, a bit quicker. And also I like the idea that once you've set up the function in your calculator, you know, you can just keep changing the number in there, and that makes it a bit quicker too. If you think about ways to use Excel spreadsheets to do this, that Newton Maths, that might, yeah, that's right. So you've got sort of loop going on. Yeah. If you set up a routine, you could try it on Excel to try and perform something like this. You could, so you put in the previous value and just go through it again, but then you'd have to come up with some stop routine, you know, when the significant figures is the same, or if the percentage error is less than a certain amount. So you could use a percentage error idea, yes, but if you wanted to set up something to do it automatically on a computer, say, you would have to get some sort of stop routine, or it would just do it forever. But this would lend itself quite nicely to some sort of computer program to do it. Okay, let's have a look at the function that we've just plotted. Here it is. I put it on autograph, and so that's our root that we're looking for here. For this particular function, the fact that it's a quadratic, a cubic, which you can see if we look here, might have made you think that possibly the curve will look like this. This is a classic cubic. And if I were to change the values in there, particularly the constants at the end, I could shift this whole cube up, and so that in fact I could have potentially 3 roots. But in this particular example, I've only got 1. So I am homing in on the only root. If you're interested in roots only in this side, which is possible, i.e. positive values, particularly at this time we were talking about, then the fact that I might have a couple of roots over here and then that one here, I could safely ignore any negative results because they're not relevant. Can you think of any problems that there might be with this procedure, other than what we've mentioned already in the previous one? Time consuming, there may be no roots, maybe more than 1 root. Still got the problem of our first guess. If you think about how we arrived at this in the first place, it was using the gradient to give us a better solution. Well, it uses the fact that the gradient is going to give us a value for x1, which is actually close to the root. To see if it does, yeah. Yeah, so you may need to sketch it, and if you've got access to software to sketch it, like Autograph, then why bother to go through it? Just use the software, okay? So what we are assuming in this case is there's a big assumption in Newton Raphson, and that is that this gradient method will give us this. If I go back to here, let's say our curve went up like this. Let's put it over here so it's not in the way, like that, and I find the gradient here. So I guess this value here and find the gradient. We know the root's here somewhere, but if I draw the gradient curve, doing that, it actually goes over here. And it could be worse, couldn't it? And so we're relying on the fact that the gradient is going to help us to get to the root a bit closer, and it might not, particularly if our first guess is a long way away from the actual root. The better our first guess, the better. Yeah. Yes, that's right. Yeah, yeah. Or your first guess was over here somewhere, then the gradient would actually be telling us that the root is, that's the next place to go for our route, over here. In fact, you're going the wrong direction. So your first guess is critical when you're using Newton-Raphson. So you could find yourself zigzagging all over the place with this Newton-Raphson. So if you're a long way in your initial guess, you can be in problems with Newton-Raphson. So in practice, if you're using Newton-Raphson and you're finding that you're flip-flopping positive, negative, and it seems to be getting worse and worse, your first guess isn't very good, and you need to go back and rethink your first guess because you're not near enough to the root. So you can't rely on Newton-Raphson to get you the result, because if you think about it, we've got this formula, and I said just think of a number and put it into this thing and it will home in on it. Not necessarily. Okay? You can't just think of any number and it will work, because the gradient method means that you might end up with problems. Okay? That is Newton-Raphson and the bisection method. So what we need to do now is just practice.